the Sky This Month with your host, Dave McDonald.
Welcome to the Sky This Month. I'm your host, Dave McDonald, and this is August 2022, and it's a great, exciting month. The big news is the James Webb Space Telescope, of course, and in a moment I'll be introducing to you our guest for the show, Kelly Beatty, who is the senior editor for Sky and Telescope magazine. We also have Saturn planet being in opposition August 14th. We have the Perseid meteor shower. We'll be talking about that. There's all kinds of, obviously, constellations and stars to talk about. We'll talk more about that at the end of the show, as well as where can you go to find the Eclipse Mobile this month. But right now, top of the show, it's about the James Webb Space Telescope that you can see behind me and behind us. So I want to welcome Kelly Beatty to our show.
Great to be here, Dave. Great to be back.
Always good to have you.
Yeah.
And so exciting things are happening with the James Webb Space Telescope. It made it, it got there, and we're going to have, in previous shows, in previous months, we've kind of milked you along a little bit what the steps are. We're going to kind of review a little bit about the Space Telescope and the importance of it, and why do we even spend $10 billion on such a thing?
Why indeed?
Yeah, that is the question. So one of the things, Kelly, that I understand is that James Webb is big on the infrared area.
That's right. So we're going to sort of coax everybody along here with a little review, a refresher of the electromagnetic spectrum. And you know, people are used to seeing visible light. This is what our eyes perceive. And infrared light, infrared energy, is part of the spectrum. So we're going to click through some of the slides here and kind of give you a sense. This is the electromagnetic spectrum. The visible light that we see is just a slice of it. Imagine you come up to a stove top, right? You've been cooking. Mm-hmm. How do you know if it's hot or not?
Well,
put your hand near it.
Yeah,
you can't see by eye, but you can sense it because of the infrared. The heat tells your hand it's still hot. This is what the James Webb Telescope is all about. It's about this infrared heat. And so what you're seeing here, this is the slice, that sort of those orange bars is where the Webb telescope will be viewing. It is a different area of the spectrum than the Hubble telescope looked at, for example.
Right. And we can see that to the bottom left,
that's right.
The HST is the Hubble Space
That's right.
Telescope.
Over here is Hubble Space Telescope, and here's James Webb. This is not the first time we've launched an infrared telescope, but it is certainly the biggest and more capable. So why infrared? Because everything gives off a little bit of heat, even if it's cold. Here's a couple of cute pictures, meerkats and a crocodile. And when you look at them in the infrared, the meerkats, because they're warm-blooded mammals, give off a lot of heat. Even though they could be in the dark, and you could still sense them because of their heat. Not so much for the crocodile. Well, the same thing applies in space. A lot of interstellar and intergalactic space is full of objects that are dusty. And they might be cold to our eyes. They might not actually give off any light that we can see, but they're probably giving off some heat. And this is a great case in point. This is a famous picture of the Eagle Nebula taken by the Hubble telescope called the Pillars of Creation. Yeah. And those dark columns that you see here on the left, these are dense columns of dust. And you can't see through them. But if you could look in the infrared, as these other images show, you can now start to peer into these dense.
And what instrument was used for the near?
So
these
are
infrared?
This is not the Webb. This is a previous spacecraft, probably the Spitzer Space Telescope. So this is the power of the infrared. It shows us things that would otherwise be invisible, say to the Hubble telescope. But there's another reason to study the infrared, and that is that it allows us to look back in time at the earliest parts of the universe. Now here again is a little graphic. The thing about the universe is it's expanding. And I wish I had brought my slinky, right? As you stretch a slinky, as you move one end apart from the other, the space between the coils spreads out. And so as things expand in the universe, what starts out as visible light coming from some distant galaxy, as it recedes far away from us, that wavelength gets shifted to longer and longer wavelengths so that it's no longer visible, it's now in the infrared.
And this expansion of the universe, which we know is not only expanding but is accelerating, it's only like 30-year-old information, like the
That's right.
1990s.
So if you want to see a galaxy that's on the other side of the universe, you don't look for it at visible light. You look for it at infrared light because it's been shifted. The waves have been stretched out. And so that
because the infrared wavelengths are longer
than
visible light.
Right. So here's our comparison. It's not only is the James Webb Space Telescope looking at a different area, a different part of the spectrum, it's also a lot bigger. And the way telescopes work, Dave, I know you know this, but maybe not all of your viewers do.
That's what we're here for.
The physics of telescopes are that the bigger around the collecting area is, yes, you collect more light, but you can also see finer detail. It's just the way the physics works.
It allows you to have a higher resolution.
That's right. You can see finer and finer detail in whatever you're looking at. And so that's why the Webb telescope was designed to be so big. It collects more light so it can see fainter objects, but it can also see them with more detail. Now, it actually under construction. It's not a single mirror. It's actually a whole bunch of mirrors that are stuck together to create an array. And so in order to collect all the light, they have to be very accurately positioned so that all that light can be brought to a single focus. One of the things about the Webb telescope that's unique and has not been done before, it's got this 5-layer blanket that protects it from the sun. Now remember, I said that infrared is heat radiation. So it doesn't do you any good to look for something that's faint and only barely glowing in the infrared if you're swamped with sunlight or if your spacecraft is really hot.
So in this case, the blanket is not to keep things warm, but in this case, the blanket is to keep the instrument cold.
That's right. And this schematic shows you what's going on. The sun can be shining on one side of the blanket, at a temperature well above boiling point of water. But on the dark side of that blanket, 5 layers later, it's hundreds of degrees below zero. And so this is great because these sensitive detectors need to be super cold in order to pick up these very feeble little glows in the night sky.
So if you're trying to detect something that is at, let's say, minus 350 Fahrenheit, we need to be colder at like minus 390 Fahrenheit to be able to detect it.
And that goes for not just the detector, but all the electronics, anything around this that is not cold will create noise that will swamp the image. So this is what the Webb telescope kind of looks like unfurled in space. It's collecting this light and bringing it to a focus. All the science instruments are back here behind it, behind the mirrors. And it's up there now and it's working. Now, it hasn't been up that long. It was launched, it's been a 40-year process to get this up into space. Just like with Hubble, there were a lot of stumbles, there were a lot of cost overruns, a lot of technological challenges. But last December 25th, it was launched into space, and it wasn't launched by NASA. It was launched by the European Space Agency on a big, powerful rocket called the Ariane 5. And the reason is that NASA itself did not have a powerful enough rocket to launch this big payload. They needed something that was beefy and dependable, and the Ariane came through. So now, this telescope, unlike the Hubble telescope, which circled Earth and still circles Earth, can you believe we're almost a third of a century since the Hubble Space Telescope was launched? 1990. Hard to believe.
True. That's true.
The Webb telescope is nowhere near Earth. It's actually about 1 million miles to the down-sun side of the Earth. You can see its position right there. It's in kind of a gravitationally stable watering hole in space, if you will, where it will stay in that position. And the reason we want it so far away is that we don't want the Earth and its heat getting in the way of making the observations.
And that's called Lagrange point 2.
Right. By Pierre Lagrange, who was the mathematician who deduced that there are these 5 points in any three-body system, as we call it.
Where you can just hang out.
Where you can just hang out. So, I don't know how we're doing for time.
Yeah.
We had a little video.
We got the video. Are we good to go with the video clip on the unfurling of the James Webb Space Telescope?
Let's have a listen and a look. You can see here that it had to be folded up like an origami spacecraft to fit inside the nose cone of that rocket. And then on its own, after being commanded by Earth, it slowly unfurled. First, the telescope was extended. You can see it's kind of collapsed on itself there. And then right at the end, the rest of the structure of the telescope popped out. And then in the months after that, NASA went through a lot of effort to make sure that everything was aligned and still working the way it should have been. There were so many ways that it could have failed.
Just it's like with 344 points
of single point failures. Yeah, right, single point failures. So there it is. It took a lot of effort. It's out in space, and after several months of tests, about a month and a half ago, it was ready to go. It was ready to start doing science.
And what are we going to explore with this space telescope?
Well, I'm glad you asked.
Oh.
There's actually a whole universe, if you will, of things that it wants to look at. But really, at its core, the telescope will be looking at the very distant and the very close by. Okay, so let's kind of explore that. I'm going to skip through a couple of these. This is, we think that the universe is 13.7 billion years, and if we can see back across the universe, we can see much younger objects than are close by, because it's a time machine. The deeper, the farther away you look, the farther back in time you look. So this is a Webb telescope image, one of the first. And it's what we call a gravitational lens. So let me kind of unpack this. All the white things you see here, these white objects, are galaxies. They're about 4.25 billion light years away. They themselves are a very long ways away. But those galaxies, together with the dark matter that envelops them, is acting like a lens, like it's bending gravity. And so all of these faint little smears that you see here, these little stretched out, distorted things, are even more distant galaxies.
And they look like they have a little curvature.
They do, because they've been warped by this lens.
Bent and warped.
So this is showing you kind of the power of the telescope. The image on the right here is at near infrared wavelengths. On the left, we're looking deeper into the infrared. And the objects here that look kind of orange are very, very distant galaxies early in the history of the universe that are full of dust. The blue ones are full of stars. We're going to come a little bit closer now, okay? This is now a group of galaxies that's only 290 million light years away. Only. They're famously called Stephan's quintet. They were discovered in the 1700s. And again, here's two pictures from the Webb telescope in the infrared. Now, I mentioned that you can't see infrared. So what they do is they take these wavelengths that they've recorded on the detectors, and they assign them to a visible light channel, a red or a green or a blue, so that we can make pictures out of them. And that's what you see here. But that's not why I'm showing you this.
Yes.
One of the great powers of the Webb telescope is not just to take pictures, but to take spectra. And by spectra, we mean if you look at objects in very specific wavelengths, they tell us what the composition is.
It's kind of like the fingerprints of the element.
That's right. Or the molecules, right?
Yes.
So in this case, we're looking at hydrogen and iron. And so the Webb telescope can look at an object and then dissect its spectrum, its rainbow, and tell us what's in there. Not only that, it can use that same spectral power to tell us whether things are moving toward us or away from us. And this is just another example. We're going to kind of come closer to home. This is in the Carina Nebula. None of these objects we can see in the northern hemisphere, by the way. You have to go down into like Argentina. And what's showing here, this is a dense cloud of interstellar gas that's being eroded away by stars. You can see right up here, there's a little spike right there. Out of view, outside are really powerful young stars that are eroding away this cloud that they were born from. Here's another example. This is in the center here is a bubble of gas that a star has lit up, and its energy is creating a bubble around it, sort of clearing the void.
Now, and this is a star that has gone supernova?
No,
this one is not.
In fact, this is a very young star. So if you imagine the star being born inside a cloud, when it lights up, it's like a flare, and it blows away all the gas around it to create a kind of hole in the cloud just by the strength of its intensity and energy.
It's pushing matter away.
Exactly.
Yeah.
And over here is the same thing, but now at a deeper infrared. And now you notice there's actually a second star there in the middle. Hadn't been known before. So this is a discovery.
And that's the Webb telescope.
That's right. Now I'm going to kind of jump through this here. What I want to show you is that a very powerful technique, believe it or not, you're going to be astounded, but lots of stars have their own solar systems, their own sets of planets around them. And so we can't see those planets. We can't, the stars are too bright, they're too far away, but we can detect them when a planet crosses in front, directly in front of a star. It actually blocks part of that star's light. And you can see it here in this curve. We see it as a dip in the output of the star. And it can be very diagnostic. It can tell us, those dips can tell us if it's a small star and a big planet, or a big star and a small planet. We learn a lot. We learn that those planets exist. We can't see them, but we know they're there. Webb is going to use that technique, that transit technique, and it's going to watch planets go in front of a star. And because the star's light is going past the planet and maybe through its atmosphere if it has one, this spectral power will allow us to actually detect the gases in the atmosphere of that planet, even though we can't see the planet. Now this is a cartoon that kind of shows how that might work, but this is real data from the Webb telescope of a planet that's more than 1,100 light years away from us, called WASP 96b. That's Wide Angle Search for Planets. That's the project. And what I want you to show here, this is an infrared spectrum. And everywhere you see a bump there, that bump is due to water in the atmosphere of this planet.
And at the bottom on what we would call the x-axis is the wavelength of light measured in microns.
In microns. And
a
all of those
micron is
wavelengths,
a
that whole
millionth of a
spectrum,
meter.
that whole spectrum is in the infrared. Visible light is farther over to the left, off screen here. Mm-hmm. And so we knew that this planet had water in it, but in its atmosphere, but we didn't know with this kind of precision that how much water from the heights of those bumps, we can determine how much water is in the atmosphere of that planet.
And those vertical lines at each white dot are like the error bars.
That's the error bar. That's the.
It could be that's
a little
kind
bit
of the
higher,
range,
a little bit lower.
and we have the blue line is the best fit of the data.
Exactly that. Exactly that. So this is just a taste of the very first things that we're getting from the Webb telescope, and I can tell you there's more to come. After the Big Bang, there was no light. It was super hot. It was millions of degrees. But there was no light, because in order to have light, you have to have something emit that light and have that light travel from point A to point B, right? It was only after about 400,000 years that the universe in its embryonic state had cooled enough to form atoms. Atoms of
Which allowed these atoms to kind of come together.
When
it was too hot, they were
also
moving around too much.
Also, the reason that we have light is that atoms have been excited to give off energy at certain wavelengths, certain packets of light, certain packets of energy, photons. And so once the universe cooled enough, then we were finally able to see light. Light was able to pass through the atoms and escape. And so one of the goals of Webb is to look farther and farther back in time. By looking at more and more distant galaxies, that light therefore has been traveling even longer to reach us. And so it started off even earlier in the history of the universe. And the goal here is to try to see back in the infrared to the very first stars, the very first galaxies, something that we've not been able to do to this point, but with the Webb Space Telescope we have a chance.
Yeah, and we can see here the Hubble Ultra Deep Field. That was kind of the limit of distance away, and now with the James Webb Space Telescope, we're going to be looking into the first galaxies. And the first stars.
We're not going to be able to see the Big Bang itself, right? Because there was no light. But we will try to see, because as the universe cooled, not only did it form these atoms, but then the universe started to it was not so homogeneous anymore. It had like little areas that were denser and less dense. And in the denser areas, things started to come together and eventually form those first stars. They condensed into the stars and the galaxies that those billions of years ago led up to what we see today. What we see, when people think of a galaxy as this, like the Milky Way, this big, beautiful pinwheel spiral galaxy with arms and hundreds of billions of stars. That isn't how galaxies started. They were kind of little oddly shaped wrecks, you know? They didn't have the beautiful structure. And one of the things that we've learned to this point, is that over time, these little small starter galaxies combine with each other. They collide with each other, and they form ever larger and more organized systems. And so we're trying to look back in time to see what was the starter kit for the universe. And that's what Webb will do.
Nice. So exciting, so exciting. And thank you so much,
Kelly, it's great to be back, yes.
On the show, and for all the depth of information you shared. And as you said, there's going to be a lot more to come. So we'll be back in just a bit and tell you about what's going on in the night sky, what you can see in your own backyard. Again, thank you, Kelly. Hope you enjoyed that with Kelly Beatty. Amazing things that the James Webb Space Telescope is doing and will do. Hey, I want to tell you where you can find the Eclipse Mobile this month in August. The Eclipse Mobile, specially designed with the 2024 total solar eclipse in mind for Coos County, New Hampshire. And you can look it up, and it crosses the United States. But just to let you know, where will we be? Well, Cobb's Cook, Bay, Maine State Star Party. Get it down. You can look it up on the internet. It's spelled right there, Cobb's Cook Bay, Maine State Star Party. Friday, August 26th, Saturday the 27th, and Sunday, August 28th. I'm going to be doing a presentation at 1 o'clock on Saturday afternoon. Saturday afternoon, I'll be talking about the stellar graveyard. Stars are born, they die. How do they die? There's 3 major catastrophe types of events that can happen. Stay tuned, 1 o'clock. Then 2 o'clock, Rick Yames, who is the proud chief pilot of the Eclipse Mobile, he is going to be speaking along with myself about the 2024 total solar eclipse. It's April 8th, 2024. You don't want to miss it. You got to find out all about it now, or it's going to be too late. We want no child left inside. Okay? So, don't miss that. The Perseids are coming August 10th to the 14th. Now they start sooner and they go later, but I've kind of bookend these dates to kind of help you find the best opportunity to see the most, okay? So the Perseid meteor shower, it's a favorite every summer. So next slide, I'm going to show you a little bit about what it has to do with. There's a comet called Comet Swift-Tuttle, and this comet goes through every once in a while. It passes through about every 3 years, 33 years, around the sun. It leaves a trail of dust, and you can see the motion of Earth here as it goes around in January and February, etc., and we come around to, we get back to July, and in August we have this point where after July, before we get to September, we have this point where Earth passes through this debris trail, and when Earth passes through this debris trail around August 12th or 13th every summer, we get this meteor shower. Okay, so check this out. The night of August 11th, late night, early morning of the 12th, is the prime time for the meteor shower proper. But we have a full moon in the way. So if you want early, like before midnight type hours on the 11th, or a little after midnight on the 12th, that's fine, but keep in mind the moon is going to be glaring. It will allow you only to see the brightest meteors. So I'm making this suggestion right here. And this suggestion is on August 11th, early morning, like 3:30 a.m., the moon is getting close to setting. So the full moon is going to be getting out of the way, and you'll have another hour or hour and a half or so of dark skies to see the most meteors that you're going to be able to get to see. So that's a suggestion for you. But if you really want to see meteors, you want to get the moon out of the way. And so the moon is going to be setting shortly after 3:30 a.m., early morning, August 11th. I think that's going to be your best shot. But again, a day before, a day after, whatever is convenient for you. And what I have here is this that looks like a wishbone. That's the constellation of Perseus. You can see that we're facing northeast, 3:30 in the morning. We're facing northeast. Capella, very bright star. Scares me to think about that. Heralds the winter sky. And this sideways wishbone is Perseus. And then this W shape, we're going to get back to this in a little bit, is the constellation of Cassiopeia. And the radiant, where most of the meteors are going to appear to come from, is right here. Okay? So that's a little tour of that part of the sky. Next, we have Saturn. Saturn is going to be in a position we call opposition on August 14th, which means as the sun sets, Saturn is going to rise. And it's going to be visible all night. I mean, it's great. Weeks before August 14th, weeks after is still fine, but the date of opposition, prime time, is August 14th. And what opposition means is we have the sun, we have Earth, and Saturn is on the opposite side of the sun. Earth is in the middle, sun on one side, Saturn is on the other. That's what opposition means. Next slide shows you where you can find, we're on August 14th, 10 o'clock in the evening, facing southeast. So face southeast, and the brightest object you're going to see in the sky facing southeast, close to the horizon, is the planet Saturn, shining at a magnitude of about 0.2, which is pretty bright. About as bright, maybe a tad brighter than Altair, which I'm going to be talking about in a moment. And the reason I also chose the 14th, Saturn is in opposition, but notice over here, Jupiter is just rising at 10 o'clock above the eastern horizon, and the moon is nearby. This is going to be a pretty sight. A night before, the moon is going to be over here, and the day after, on the 15th, the moon is going to be down lower. The moon is in continual motion. Okay, so that's where to find Saturn on the 14th. Next, I want to mention the southern sky as you face south. I just want to point out the familiar teapot asterism here. You can see the teapot. Here's the base. You have the handle. You have the lid with the knob right here. You have the spout. That's the constellation of Sagittarius. And to the right is the heart of the Scorpion, Antares, bright red star. And we can go to the next slide and see the artwork that goes along with this. And you can see now the artwork that goes with it. With the next slide, right here, we see the centaur right here, Sagittarius, the archer, with his arrow trained on the heart of the scorpion, right there. Now, above Scorpius, you have to look it up and check out. The stars are not super bright, but this is a huge constellation called Ophiuchus. It is the 13th member of the zodiac, and its legs go down into the ecliptic, and it is part of the zodiac proper. Next, we look at overhead. Overhead all month, the brightest star that you're going to see overhead is Vega. And then you have Deneb, which is the tail of the swan or the top of the Northern Cross. Altair, the wing of the eagle. We saw Altair on the previous slide. And so this makes up what we call the summer triangle here. So next slide, you can see the artwork with the lyre. You can see the swan, and you can see the eagle. Neat little constellations. that are nearby. To the left of Altair is Delphinus, the dolphin, and Equius, the little horse here. And then there's an arrow called Sagitta. Very cool. Okay, next on our show is the sky without any lines or artwork, and this is where you need to be able to find things. So Altair, Vega, Deneb, overhead makes like a pizza slice. It's the summer triangle. Next slide, we're going to come back to reminding you about the Perseid meteor shower. August 11th is just a suggestion. 3:30 in the morning, let the moon, excuse me, let the moon set or get close to setting. But I want to point out to you, as you look north, you're going to see the Big Dipper. The two end stars, Merak and Dubi, point to the North Star, which is here. And then if you keep on going, you come to that W shape, which I showed you earlier, the Cassiopeia, the Queen. And between Cassiopeia and Perseus is where the radiant of the meteor shower is. So finally, I want to show you this slide that shows a close-up of Cassiopeia. But if you take these two middle stars and you make like a straight line, you'll be able to see it just barely with the unaided eye, this double cluster. You'll see a couple little fuzzy spots. Binoculars will bring it out. And that's the famed double cluster between Cassiopeia and Perseus. A great thing to be looking at while you're enjoying the meteor shower and while you're waiting for some meteors. And binoculars will be a big help. So I hope that you enjoyed the show. And I'm Dave McDonald for The Sky This Month. You can email me at astromannh@gmail.com. Be happy to answer any questions you might have. Hope you enjoyed the show.